Hello again. This is Math 1120 coming to you from the College of DuPage, and the title of this lecture is Force, Mass, and Newton's Three Laws. As always, be an active learner when you watch this video. By way of introduction to the concept of force, and later we'll talk about mass. A force is a push or a pull. So you can be pushing, and that's a force, or you can be pulling. And here we're thinking about this box is at rest, and so you could either push it or pull it and start it moving. So a force can be thought of as a push or a pull. A force is an interaction between two objects, or between an object and its environment. And a force is a vector quantity. Here you are pushing this to the right, and here you're pushing this to the right. But I could be putting my hand on the other side and pushing it to the left. So force is a vector quantity with both a magnitude and direction. And we can have contact forces like this, but we can also have forces that act at a distance, and gravity is an example of a force that acts over a distance. The fundamental role of a force is to change the state of motion of an object on which the force acts. The key word is change. Newton's first law of motion states, every object continues either at rest or at a constant speed in a straight line unless it is forced to change its motion by forces acting on it. So forces cause a change in motion. So if an object is sitting at rest, there's no force on it, and that means that the sum of the vector forces has to be zero, so it remains at rest. If it's moving at a constant velocity and there are no forces, for example, no friction, they will continue to move indefinitely. An interesting corollary of this statement is once an object has been set in motion, no net force is needed to keep it moving. In other words, an object acted on by no net force moves with constant velocity, which may be zero, and thus zero acceleration. Now, the tendency of an object to remain at rest, or to keep moving once it's set in motion, results from a property called inertia. That's what you feel when you're behind home plate and a fastball hits your glove. The baseball really wants to keep moving. The tendency of an object to remain at rest is also due to inertia. And you may have seen a tablecloth yanked out from under china without anything being broken. As the tablecloth slides, the force that exists on the china isn't great enough to make the china move appreciably. The quantitative, that is, numerical measure of inertia, is a physical quantity called mass, which we're going to be discussing in this section as well. When an object is acted on by no forces, or perhaps we have several forces whose vector sum is zero, we say the object is in equilibrium. So if all the forces add up to zero, it's in equilibrium. Its motion does not change, and that means that if you add up the forces in an x direction or a y direction, those also are zero because it is in equilibrium. Let's look at a problem to test your understanding of these concepts. Your team decides to play leaf blower ice hockey. Use your blower to apply a constant force that accelerates the puck in a straight line. An opponent escapes up and uses her blower to apply an equally strong constant force directed opposite to yours. Her force, acting together with yours, would cause the puck to. You have four choices. You know what to do. Let's see how you did. Force from your blower alone causes the puck to accelerate because it was a force. The force from your opponent's blower is equal in magnitude and opposite in direction, so the vector sum of the two forces is zero. A puck that is acted on by zero net force has no acceleration. Thus a puck does not slow down or halt, but instead moves with constant velocity in accordance with Newton's first law. The correct answer is D. That also might mean that it's not moving at all, because a constant velocity of 0 is still a constant velocity. Here is a caveat too, that here in this drawing you see that a truck is moving with constant velocity relative to the person on the ground. Now that means that for the person on the ground and the truck, since they're constant velocities, Newton's first law is obeyed in both frames because they are called inertial reference frames. If a plane was accelerating, Newton's first law is not obeyed, and these are non-inertial reference frames. This is beyond the scope of our course, but this is something that Einstein studied a great deal, and you should know it exists. But we will tend to work in inertial reference frames. Now we're going to do kind of a little bit of an experiment, and suppose again we'll talk about the ice hockey puck. And what we'll do is we'll have a certain force, a pull, and so we'll have a pull that's showing to be, I'm just going to call that 6 units, and we can measure the acceleration of the puck. And what we find is a constant force causes a constant acceleration. Notice both of those are vectors. And in fact, the force is operating this way and the acceleration is also that way. So the direction of the acceleration is in the direction of this force. Now if we double this force, so we're doubling this force and we have twice the force, we find that there is twice the acceleration. We also find out if we half the force, we half the acceleration. And I guess that means that the 0 on this scale actually is there at 12 o'clock. So you might think about this as being 3, you might think about this as being 6, and you might think about this as being 1.5. So you see what happens is that the force and acceleration are directly proportional. That means that the acceleration is equal to the force over the mass, and that could be written as F equals ma, which is called Newton's second law. Now that means that the net force is equal to the mass times the acceleration. And again, it's important you think about that being a net force. So you see, this m here is the mass. So the concept of mass is a familiar one. If you hit a table tennis ball with a paddle and then hit a basketball with the same force, the basketball has a much smaller acceleration because it has a greater mass. When a large force is needed to give an object a certain acceleration, the mass of the object is large. When only a small force is needed for the same acceleration, the mass is small. The greater the mass, the more the object resists being accelerated. Thus, mass is a quantitative measure of inertia. The SI unit of mass is the kilogram, and we mentioned this earlier. The kilogram has an official definition, but we will use that standard kilogram to define this, and that also will define the fundamental SI unit of force called a Newton, abbreviated N. So you see, now we've talked about mass, kilograms, and now we're talking about Newton, abbreviated capital N, named after Isaac Newton. This is the definition of a Newton. 1 Newton is the amount of force that gives an acceleration of 1 meter per second squared to an object with a mass of 1 kilogram. Now notice that acceleration does come in meters per second squared, and so 1 Newton is a kilogram meter per second squared. And we also have Newton's second law, which we've already sort of talked through, and that is the vector sum, or the net force, is equal to the mass times the acceleration. If the acceleration is equal to 0, the net force is 0. And the force in this equation are applied to a single object with mass m. The acceleration has the same direction as the resultant force, that is the net force. And the units are forces in newtons, mass is in kilograms, and acceleration is in meters per second squared. Again, units are important. And this is what Newton's law says in component form. So since there's no acceleration at all, there's no acceleration in the x direction, and there's no acceleration in the y direction, or this is the vector component thing. If you add up the vectors in the x direction, that gives you the mass times the acceleration in the x direction. If you add up the forces in the y direction, that is the mass times the acceleration in the y direction. And we will usually use this to solve our vector problems, as before. All right, let's look at a problem here. And so what we're going to consider is a very simple application of Newton's second law. A worker with spikes on his shoes pulls a constant horizontal force of 20 newtons on a box with mass of 40 kilograms, and it's on a flat frictionless surface. Consider that's a frozen lake. What's the acceleration of the box? Well, here's the picture. So you got this guy that's pulling in this direction. The tension on the rope is 20 newtons. Now there are forces acting on here, because what you will come to know is that this box does have a certain weight. That is the mass times g. mg is the weight of the box. And we're going to find that there's an equal and an opposite reaction. And so the lake is, so the box is pushing down on the lake with a force of W, and that is m times g, and the lake is pushing up. That is called the normal force. That is equal and opposite because there's no movement. It doesn't fall through the lake. But you're pulling it this way, but we're assuming there's no friction. So F equals ma. So we say that when you add up the forces, it's the mass, which is the acceleration, I guess is what we wanted to find. So the acceleration is F, there's only movement in the x direction, divided by m. It's 20 newtons over 40 kilograms. Now that's kilograms meters per second squared over kilograms. The kilograms will cancel and you get 0.5 meters per second squared. The force is constant, so the acceleration is also constant. And if we were given the initial position of the velocity of the box, we could find the position and velocity of the box at any time later from equations of motion with constant acceleration, as we did before. Let's talk about that kind of situation with a ketchup bottle. So you have a ketchup bottle whose mass is 0.2 kilograms, and a bartender shoves the bottle of ketchup with an initial velocity of 2.8 meters per second squared. And there's a customer down here who wants the ketchup bottle. They slide it along, and it comes down and it stops exactly in front of this person, meaning that that the velocity is 0. And so what we want to know is, what is the magnitude and direction of the friction force that causes it to stop? Well, okay, so what was its, we're going to talk about, what its final velocity was here, its initial velocity was here. So we need to find the relationship between Vx and Ax. Well, the way to do that is to use this equation from the earlier chapter. V sub x squared is minus V sub 0 in the x direction squared is 2a, that is x minus x0. Now x minus x0 was 1.0 meters. This is 1 meter, not 10 meters. It's 1 meter, 1.0 meters. So we get 1.0 meters here. It was going at 0 at the end. This is minus 2.8, so the acceleration is minus 3.9 meters per second squared. Now the ketchup bottle still has a mass of 0.2 kilograms, so that is going to be equal to, this is m times a. So it's 20. It's 0.20 kilograms times an acceleration of minus 3.9 meters per second squared, and you do the calculation and you get minus 0.78 newtons. So that is the frictional force that causes this ketchup bottle to stop on the countertop. Let's look at another example. Now here you have a force that is, in fact, this is a mass of a electron. Now this is 9.11 times 10 to the minus 31st kilograms. That's a very small number. And you have an electrical force that is 1.60 times 10 to the minus 13 newtons. And so the question is, what acceleration is caused here? Well, A is equal to the summation of the forces. There's only one force, so does this, divided by m. Now you have to be careful with this calculation, and you have powers of 10 involved. But we get this is 1.76 times 10 to the 17 meters per second squared. That's an enormous number, but the reason that's an enormous number is the mass was very small. Let's test your understanding again. Suppose you use a rope to hoist a box of tools vertically with a constant upward acceleration. How does the magnitude of the tension of the rope compare to the magnitude of the weight of the toolbox as you lift it? You have three choices here. You know what to do. Let's see how you did. Because the toolbox has an acceleration that points upward, Newton's second law tells us the net force must also point upward. Therefore, the magnitude of the force pulling the toolbox upward must be greater than the magnitude of the force pulling it downward. The correct answer is A. This brings us to Newton's third law. For two interacting objects A and B, Newton's statement was, to every action there's always an equal and opposite reaction. That's the reason that when we had the weight of the box on the ice, that the ice was pushing back with the same weight. Newton's statement means when A applies a force to B, A itself experiences a force that is equal to magnitude but opposite in direction to that experienced by B. This law applies only to the force between two separate objects. The two forces in that equation are referred to as an action-reaction pair. And two forces in an action-reaction pair never act on the same object. That's kind of the same thing as the second statement, just said differently. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.